concept that has intrigued and puzzled thinkers for centuries. The idea that the universe, or anything at all, could come from nothing appears paradoxical, yet it has been at the heart of philosophical and scientific discussions about the origins of existence. When we think of nothing, most imagine an empty void, a space devoid of matter, energy, or anything else. However, when delving deeper, both philosophy and modern science reveal that nothing is far more complex than mere emptiness. Philosophers from as early as Plato and Aristotle questioned what nothing really meant. To them, nothing was not a simple absence, but a profound metaphysical problem. Fast forward to modern times, and scientists like Stephen Hawking have expanded the concept, particularly in relation to quantum mechanics, suggesting that nothing is not truly devoid of activity. Instead, even in the vacuum of space where nothing exists, there are still quantum fluctuations, fleeting and minuscule energy changes, suggesting that perhaps nothing isn't as empty as we once thought. This chapter will explore how both philosophical and scientific perspectives have contributed to the evolving definition of nothing, and how the concept plays a critical role in modern cosmology, particularly in understanding the origin of the universe. In the philosophical realm, the concept of nothing has evolved significantly over the centuries. Ancient Greek philosophers, like Parmenides, denied the existence of nothing, asserting that something could never arise from nothing. He famously declared, "What is, and what is not, is not." This suggests a fundamental difficulty in conceiving the idea of absolute nothingness. Aristotle, in contrast, posited that nothing was the absence of form or matter, yet he argued that something must always exist in some form because nature abhors a vacuum. Later philosophers, like René Descartes and Immanuel Kant, dealt with the problem of nothing in more abstract terms. Descartes, known for his 17th century work, proposed a dualism between mind and body, where nothing could exist in the gap between thinking, mind, and the material world, body. Kant, writing in the late 18th century, considered nothing, not only in metaphysical terms, but also in relation to human experience, emphasizing that nothingness could be linked to human perception and limitations in understanding the universe's origins. In the 20th century, existentialists like Jean-Paul Sartre and Martin Heidegger focused on nothing in terms of existential dread and human meaning. Sartre, in particular, coined the term néant to describe the nothingness at the heart of human freedom and choice. Heidegger, in his work Being and Time, 1927, explored how nothingness is central to the human experience of being, framing it as the space in which all possibilities reside. While philosophy wrestles with abstract concepts of nothing, science takes a more empirical approach. In classical physics, nothing was largely understood as the vacuum, a completely empty space devoid of matter or energy. However, in the 20th century, quantum mechanics began to reveal that even in the absence of matter and energy, nothing is still teeming with activity. One of the key breakthroughs in this understanding came from quantum field theory. According to this theory, even in the vacuum of space, quantum fluctuations occur. These fluctuations are tiny, fleeting changes in energy that spontaneously create and annihilate pairs of particles, such as electrons and positrons. This phenomenon was first formally described in the 1930s, and it suggests that even the vacuum, which we once thought of as nothing, is filled with dynamic processes. Furthermore, Heisenberg's uncertainty principle, introduced in 1927, shows that we can never precisely know both the position and momentum of a particle. As a result, even in a vacuum, there is never true nothing, because these uncertainties cause fluctuations in energy. This concept is pivotal to understanding that the vacuum of space, what we might casually refer to as nothing, is actually a seething, restless medium. Additionally, Stephen Hawking and other physicists have suggested that, under certain conditions, such as near the event horizon of a black hole, particles can escape these fluctuations, a phenomenon now known as Hawking radiation. Discovered theoretically in 1974, this process implies that something can indeed emerge from nothing, at least according to quantum mechanics. A significant component of the scientific exploration of nothing revolves around the idea of virtual particles. These particles are a consequence of quantum fluctuations, where for an incredibly short period, pairs of particles and antiparticles, such as electrons and positrons, emerge from the vacuum, exist for a moment, and then annihilate each other, effectively returning to nothing. Though these particles cannot be directly observed, their effects can be measured. For instance, the Casimir effect, first observed in 1948, demonstrates how two uncharged metal plates, placed very close together in a vacuum, experience a measurable force due to the difference in quantum fluctuations inside and outside the plates. These insights, stemming from quantum mechanics, challenge our classical intuition about nothingness, leading to the realization that even in the absence of matter and energy, the vacuum of space is far from empty. Instead, it is full of potential and fleeting moments of something. One of the most profound questions in cosmology is how the universe began. Central to this question is whether the universe could have emerged from nothing. The Big Bang theory, the leading explanation for the universe's origin, posits that approximately 13.8 billion years ago, the universe expanded from a hot, dense state. This expansion, often incorrectly visualized as an explosion, actually involved space itself expanding rapidly, creating the fabric of the universe as we know it. But what preceded the Big Bang? And can something truly come from nothing? One hypothesis, developed through quantum cosmology, suggests that the universe could have emerged from a quantum vacuum. Stephen Hawking and James Hartle proposed the no-boundary hypothesis in the 1980s, suggesting that time behaves like another dimension of space at the universe's origin. In this framework, there is no distinct moment of creation, no before the Big Bang, just a smooth transition from quantum fluctuations to the vast cosmos we observe today. This implies that nothing in the quantum sense could have led to the universe's birth. Another fascinating idea related to nothing is the concept of a multiverse, where our universe is just one of potentially infinite other universes. Some cosmologists, including Alan Guth in the 1980s, have suggested that the inflationary period in the early universe might not have been a one-time event. Instead, inflation could be happening in different regions of space, continuously creating new universes, each with its own laws of physics. In this model, each new universe arises from quantum fluctuations in the vacuum, effectively coming from nothing. This suggests that not only could our universe have come from nothing, but many universes could be constantly coming into existence, shaped by the randomness of quantum mechanics. The idea that the universe could arise from nothing presents significant philosophical implications. One key issue is the question of causality. How can something, like the universe, arise without a cause? The concept of quantum fluctuations helps address this, as these fluctuations occur without a deterministic cause, governed instead by probabilities. In the vacuum, these random fluctuations are enough to spark the creation of particles, and on a larger scale, perhaps even the universe itself. Philosophically, this challenges classical views of creation, where every effect must have a cause. In the quantum world, the very rules of causality become blurred. This has led some to speculate that the universe's existence is not only possible, but perhaps inevitable given the properties of the quantum vacuum. Furthermore, this idea intersects with debates about fine-tuning in the universe. Why do the constants of nature, the strength of gravity, the charge of the electron, and so on, seem precisely adjusted to allow life to exist? If multiple universes are continually being created from nothing, with different laws in each, it may simply be a matter of chance that we live in one that is conducive to life. Thus, nothing is far from a simple void. Whether viewed through the lens of philosophy as a profound metaphysical question, or through the eyes of science as a quantum vacuum teeming with potential, nothing plays a central role in our understanding of existence. The implications of this concept extend beyond theoretical musings, influencing our understanding of the universe's origin and pushing the boundaries of cosmological theories. As we continue to explore the mysteries of the universe, the question of whether nothing could have sparked everything remains one of the most profound and captivating challenges in both philosophy and science. The universe is a vast, awe-inspiring expanse that encompasses everything from the smallest particles to the largest cosmic structures. It includes space, time, matter, and energy, all governed by the fundamental laws of physics. One of the most profound insights that humanity has gained through the study of the cosmos is the age and size of the universe. According to the Big Bang theory, the universe began approximately 13.8 billion years ago from an incredibly dense and hot singularity. Since then, it has been expanding continuously, a phenomenon first discovered by Edwin Hubble in 1929. This expansion means that the universe is not static, but growing larger with time. When we observe distant galaxies, we see them as they were millions or even billions of years ago, providing a window into the universe's early history. The sheer size of the universe defies human comprehension. The observable universe alone, which represents the part of the cosmos we can see and study with current technology, is estimated to have a diameter of 93 billion light-years. Light, which travels at a staggering 300,000 kilometers per second, or 186,000 miles per second, would take 93 billion years to traverse the observable universe from one end to the other. Yet, this is likely only a fraction of the universe's total size, as there may be regions far beyond what we can detect due to the finite speed of light and the universe's continuous expansion. To further grasp the vastness, consider the number of stars and galaxies that populate the universe. Current estimates suggest there are approximately 2 trillion galaxies in the observable universe, each containing millions to billions of stars. Our own galaxy, the Milky Way, is relatively average in size and contains an estimated 100 to 400 billion stars. Yet, even with such staggering numbers, the universe is mostly empty space, with vast distances separating individual stars and galaxies. As large as the universe is, the study of its age and expansion has revealed crucial insights into its future. Observations indicate that the universe is not only expanding, but that this expansion is accelerating, driven by a mysterious force called dark energy. This discovery, made in 1998 by 2 teams of scientists studying distant supernovae, has led to the realization that the universe could continue expanding forever, with galaxies moving farther and farther apart until they become isolated from each other. When we speak of the universe, it is important to clarify that what we refer to as the observable universe is only the portion of the entire cosmos that we can detect from Earth, given the finite speed of light and the universe's age. The observable universe is a bubble centered on Earth, with light that has had 13.8 billion years to reach us from the most distant objects we can observe. However, due to the ongoing expansion of space, the actual distance to the edge of the observable universe is now about 46.5 billion light-years in all directions, yielding a total diameter of about 93 billion light-years. The observable universe contains everything from planets, stars, and galaxies to nebulae, black holes, and vast cosmic structures like galaxy clusters and superclusters. Despite the enormity of the observable universe, scientists believe that it is only a small part of the entire universe, which may be infinite in size. The concept of the cosmic horizon is key to understanding the limits of the observable universe. The cosmic horizon marks the boundary beyond which light has not yet had enough time to reach us since the beginning of the universe. As time goes on, we will be able to observe more of the universe, as light from more distant objects finally reaches Earth. However, the expansion of the universe means that some distant regions will eventually recede faster than light can travel, effectively placing them forever beyond our reach. At the heart of our understanding of the observable universe is redshift, a phenomenon that occurs when the light from distant galaxies is stretched to longer wavelengths as the universe expands. Edwin Hubble's observations of redshift led to the discovery that galaxies are moving away from us, providing the first strong evidence that the universe is expanding. This redshift is now described by Hubble's law, which states that the velocity at which a galaxy recedes is proportional to its distance from Earth. Another essential tool for understanding the observable universe is the cosmic microwave background radiation, CMB. The CMB is the afterglow of the Big Bang, a faint glow of microwave radiation that fills the universe and provides a snapshot of the cosmos as it appeared about 380,000 years after its formation. Discovered by Arno Penzias and Robert Wilson in 1965, the CMB offers critical evidence for the Big Bang theory and helps scientists measure the universe's size, age, and composition. The structure of the universe is dominated by galaxies, which are vast systems of stars, gas, dust, and dark matter bound together by gravity. Galaxies come in many different shapes and sizes, but they can be broadly categorized into spiral galaxies, elliptical galaxies, and irregular galaxies. Spiral galaxies, like our Milky Way, have a flat, rotating disk of stars and gas, with a central bulge surrounded by spiral arms. The Milky Way, with its diameter of about 100,000 light-years, is just one of billions of spiral galaxies. Elliptical galaxies are more spherical or oval-shaped and contain older, less active stars. They are often found in galaxy clusters and can be significantly larger than spiral galaxies. Some giant elliptical galaxies can span over 1 million light-years across. Irregular galaxies lack a distinct shape and often appear chaotic. They may be the result of gravitational interactions or mergers between other galaxies. The largest known galaxy is the IC 1101, a supergiant elliptical galaxy located over 1 billion light-years from Earth. IC 1101 has a diameter of approximately 6 million light-years, making it over 60 times larger than the Milky Way. In addition to stars and galaxies, the universe contains a variety of other cosmic structures. Nebulae, vast clouds of gas and dust, are the birthplaces of stars. Star clusters are groups of stars that form together from the same molecular cloud. Black holes, regions of space where gravity is so strong that nothing can escape, are often found at the centers of galaxies, including the Milky Way, which harbors a supermassive black hole named Sagittarius A. Stars are the fundamental building blocks of galaxies and play a crucial role in the life cycle of the universe. Stars form from the gravitational collapse of gas in molecular clouds and spend most of their lives fusing hydrogen into helium in a process called nuclear fusion, which produces the light and heat that stars emit. The temperature at the core of a typical star, like our Sun, is around 15 million degrees Celsius. Stars come in many different types and sizes, from small, cool red dwarfs, which can burn for trillions of years, to massive blue giants, which burn through their fuel in just a few million years before exploding in spectacular supernovae. These supernovae scatter heavy elements into space, which later become incorporated into new stars, planets, and even life itself. The most massive stars end their lives as black holes or neutron stars, the remnants of supernova explosions. At the largest scales, galaxies are not randomly distributed, but are organized into galaxy clusters and superclusters, which are connected by vast filaments of dark matter. These structures form the cosmic web, a vast, intricate network that stretches across the observable universe. The Hercules Corona Borealis Great Wall is the largest known structure in the universe, a supercluster complex that spans over 10 billion light-years. While visible matter, stars, planets, galaxies, makes up much of what we observe in the universe, it only accounts for about 5% of the universe's total energy content. The rest is composed of dark matter and dark energy, two mysterious substances that remain largely undetected by conventional means, but play a crucial role in shaping the cosmos. Dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, who observed that galaxies in the Coma cluster were moving too fast for the visible matter to account for the necessary gravitational forces holding the cluster together. This led to the hypothesis that there must be an unseen form of matter providing additional gravitational pull. Although dark matter does not emit, absorb, or reflect light, its presence can be inferred from its gravitational effects on visible matter. Observations of galaxy rotation curves, for example, show that stars at the edges of galaxies rotate faster than expected, indicating the presence of a massive, invisible halo of dark matter. Estimates suggest that dark matter makes up about 27% of the universe's total energy content. The leading candidates for dark matter are WIMPs, weakly interacting massive particles, and axions, hypothetical particles that interact only through gravity and the weak nuclear force, making them extremely difficult to detect. However, despite decades of research, dark matter particles have yet to be directly observed. Dark matter is essential for understanding the formation and evolution of cosmic structures. Without the gravitational pull of dark matter, galaxies and galaxy clusters would not have formed in the early universe. Dark matter acts as a cosmic scaffold, providing the necessary gravitational glue to hold galaxies together and prevent them from flying apart. While dark matter helps hold the universe together, dark energy is thought to drive its expansion. Discovered in 1998 by two independent teams of astronomers, one led by Saul Perlmutter and the other by Adam Rees and Brian Schmidt, dark energy is responsible for the accelerated expansion of the universe. Dark energy is believed to make up about 68% of the universe's total energy content. Unlike dark matter, which is concentrated in galaxies and clusters, dark energy appears to be evenly distributed throughout space. It acts as a repulsive force, counteracting gravity and causing the expansion of the universe to speed up over time. The discovery of dark energy was unexpected and has led to a profound shift in our understanding of the universe's fate. Before its discovery, scientists believed that the universe's expansion would eventually slow down and possibly reverse, leading to a big crunch. However, with the accelerated expansion driven by dark energy, it now seems more likely that the universe will continue expanding forever, with galaxies becoming more isolated over time. The nature of dark energy remains one of the greatest mysteries in cosmology. Some theories suggest that dark energy could be the cosmological constant introduced by Albert Einstein in 1917, a term in his equations of general relativity that represents the energy density of empty space. Others propose more exotic explanations, such as quintessence, a dynamic field that changes over time. Despite its elusive nature, dark energy plays a critical role in the large-scale structure of the universe and its ultimate fate. Understanding dark energy is one of the top priorities in modern cosmology, with numerous experiments and observations, including the Dark Energy Survey and the Euclid space mission, aimed at unraveling this cosmic mystery. The Big Bang Theory is the leading scientific explanation for the origin of the universe. According to this theory, the universe began approximately 13.8 billion years ago from an extremely hot and dense point known as a singularity. At that moment, space, time, matter, and energy all emerged and began expanding rapidly. Contrary to the name, the Big Bang was not an explosion in the traditional sense, but an expansion of space itself. The concept of the Big Bang was first proposed in 1927 by Belgian priest and physicist Georges Lemaitre, who referred to it as the hypothesis of the primeval atom. Lemaitre suggested that the universe had expanded from a highly compact state. In 1929, Edwin Hubble's observations of distant galaxies revealed that they were moving away from us, leading to the discovery that the universe is expanding. This observation supported Lemaitre's hypothesis and became one of the cornerstones of the Big Bang theory. The Big Bang theory has been further confirmed by the abundance of light elements, such as hydrogen and helium, which were produced in the first few minutes after the Big Bang through a process called Big Bang nucleosynthesis. These elements make up approximately 75% hydrogen and 25% helium by mass, with trace amounts of lithium. This matches the observed composition of the universe today. The theory not only explains the origin of the universe, but also provides a framework for understanding its subsequent evolution, including the formation of galaxies, stars, and planets. It remains the most widely accepted model for the universe's beginnings, although it continues to be refined through ongoing research and observations. One of the most significant additions to the Big Bang theory is the concept of cosmic inflation, a period of extremely rapid expansion that occurred just moments after the universe began. Proposed by physicist Alan Guth in 1980, cosmic inflation suggests that the universe expanded exponentially during the first fraction of a second after the Big Bang. Before inflation, the universe was so small and dense that quantum effects dominated. However, as inflation began, space expanded much faster than the speed of light, smoothing out any irregularities and creating the conditions we observe in the universe today. Inflation solved several problems in cosmology, including the horizon problem and the flatness problem. The horizon problem refers to the observation that regions of the universe that are now far apart appear to have the same temperature, even though they should not have had enough time to exchange information or energy. Inflation solves this by suggesting that these regions were once close together before being stretched apart by the rapid expansion of space. The flatness problem arises from the fact that the universe appears to be geometrically flat, meaning its density is very close to the critical value that separates a universe that will eventually collapse from one that will expand forever. Inflation explains this by showing that the rapid expansion would have diluted any initial curvature, making the universe appear flat on large scales. Inflation also provides a mechanism for the formation of cosmic structures. During inflation, tiny quantum fluctuations in the density of matter were stretched to macroscopic scales. These fluctuations later became the seeds for the formation of galaxies, clusters, and the large-scale structure of the universe. The evidence for these primordial fluctuations can be seen in the temperature anisotropies in the cosmic microwave background radiation, first detected by the COB satellite in 1992, and later measured in greater detail by the WMAP and Planck satellites. After the inflationary period ended, the universe continued to expand, but at a much slower rate. As the universe cooled, matter began to form, and the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, became distinct. The temperature of the universe during this time was about 10 to 27 degrees Celsius, but it cooled rapidly as space expanded. As the universe cooled after the inflationary period, the energy from the Big Bang began to transform into the fundamental particles of matter. In the first fraction of a second after the Big Bang, the universe was filled with a hot, dense plasma of particles, including quarks, leptons, such as electrons, and photons. The temperature at this stage was approximately 10–15 degrees Celsius. In the first 10–12 seconds after the Big Bang, The universe was so hot and dense that quarks, the building blocks of protons and neutrons, could not combine to form particles. Instead, they existed in a state known as quark-gluon plasma. As the universe expanded and cooled, quarks began to combine to form protons and neutrons. About 10 to the negative sixth seconds after the Big Bang, protons and neutrons had formed. These particles are known as hadrons, and this period is called the hadron epoch. During this time, the universe was still too hot for atomic nuclei to form, so protons and neutrons remained free in a hot, dense plasma. Lepton epoch. Approximately 1 second after the Big Bang, the universe had cooled to a temperature of about 10 billion degrees Celsius. During this period, electrons, which are leptons, and neutrinos dominated the energy of the universe. Protons and neutrons still existed as free particles, but the universe was not yet cool enough for them to form atomic nuclei. Big Bang. Nucleosynthesis. Between 1 second and 3 minutes after the Big Bang, the universe had cooled to about 1 billion degrees Celsius, which allowed for the formation of the first atomic nuclei in a process known as Big Bang nucleosynthesis. During this process, protons and neutrons combined to form the nuclei of hydrogen, H, helium, Chi, and trace amounts of lithium, Li. The exact proportions were about 75% hydrogen, 25% helium, and tiny amounts of other light elements like lithium. Big Bang nucleosynthesis was responsible for creating the light elements that we observe in the universe today. Heavier elements, such as carbon and oxygen, were formed later in the interiors of stars through the process of stellar nucleosynthesis. By about 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms, a process called recombination. This event marks the point at which the universe became transparent to light, allowing photons to travel freely through space. The cosmic microwave background radiation we observe today is the afterglow of this event. While the Big Bang and cosmic inflation explain the universe's origin and early expansion, another mysterious force is responsible for its current behavior: dark energy. Discovered in 1998 by 2 independent teams of scientists, dark energy is the force driving the accelerating expansion of the universe. Before this discovery, scientists believed that the universe's expansion, driven by the energy of the Big Bang, would eventually slow down due to the pull of gravity. Some even speculated that the expansion might reverse, leading to a big crunch. However, observations of distant type Ia supernovae showed that galaxies are not just moving away from us, but are doing so at an ever-increasing rate. This surprising discovery earned Saul Perlmutter, Adam Rees, and Brian Schmidt the Nobel Prize in Physics in 2011. Dark energy is thought to make up about 68% of the total energy content of the universe. Despite its dominance, dark energy remains one of the biggest mysteries in cosmology, as it has yet to be directly observed. However, its effects on the large-scale structure of the universe are evident. Dark energy acts as a repulsive force, counteracting gravity and causing the expansion of space to accelerate. There are several theories about the nature of dark energy. One possibility is that dark energy is the cosmological constant, L, a term introduced by Albert Einstein in 1917 in his equations of general relativity. Einstein originally included the cosmological constant to maintain a static universe, but he later discarded it when it was discovered that the universe was expanding. However, the concept of a cosmological constant has been revived to explain dark energy as a constant energy density filling space. Another theory is that dark energy is related to quintessence, a dynamic field that changes over time. Unlike the cosmological constant, which remains constant, quintessence would vary in strength as the universe evolves. Dark energy has profound implications for the fate of the universe. If dark energy continues to dominate, the universe will keep expanding at an accelerating rate, leading to a future scenario known as the Big Freeze or heat death. In this scenario, galaxies will move so far apart that they will no longer be able to interact, and the universe will become cold, dark, and lifeless. However, if the nature of dark energy changes over time, other possibilities exist. In the Big Rip scenario, dark energy could become so strong that it tears apart galaxies, stars, and even atoms. Alternatively, if dark energy weakens or reverses, the universe's expansion could slow down and eventually lead to a big crunch where the universe collapses in on itself. The Big Bang Theory provides a comprehensive explanation for the universe's origin and early evolution, from the singularity that marked its birth to the formation of matter and light elements. The discovery of cosmic inflation solved many of the mysteries surrounding the universe's early expansion, while the formation of the first atomic nuclei during Big Bang nucleosynthesis laid the foundation for the chemical elements we observe today. Finally, the discovery of dark energy has revolutionized our understanding of the universe's future, revealing that the expansion of space is accelerating and that the universe's ultimate fate remains uncertain. The interplay of dark energy, dark matter, and the laws of physics continues to shape the cosmos, driving ongoing research into the deepest mysteries of existence. Galaxies are the fundamental building blocks of the universe. They are vast collections of stars, gas, dust, and dark matter bound together by gravity. The formation of galaxies is one of the most important processes in the universe's history, giving rise to the structure and distribution of matter we see today. The formation of galaxies began shortly after the Big Bang, which occurred around 13.8 billion years ago. After the initial expansion of the universe, it cooled enough for matter to begin clumping together under the influence of gravity. During the early stages of the universe's evolution, small fluctuations in the density of matter, which were imprinted during the inflationary period, provided the seeds for galaxy formation. These fluctuations were detected in the cosmic microwave background, CMB radiation, first discovered by Arno Penzias and Robert Wilson in 1965. As the universe expanded and cooled, dark matter began to form structures known as dark matter halos. These halos acted as gravitational wells, pulling in ordinary matter, baryonic matter, which eventually formed stars and galaxies. Dark matter is a mysterious substance that does not emit light or energy, making it undetectable by conventional means. However, its presence is inferred from its gravitational effects on visible matter. It is estimated that dark matter makes up about 27% of the universe's total mass energy content. The formation of galaxies occurred over billions of years, and the earliest galaxies likely formed around 1 billion years after the Big Bang. These early galaxies were much smaller and more chaotic than the large organized galaxies we see today. Through a process known as hierarchical merging, smaller galaxies collided and merged to form larger galaxies. This process continued for billions of years, leading to the formation of massive galaxies like the Milky Way, which is estimated to have formed around 13.6 billion years ago. There are several different types of galaxies, each with distinct shapes and characteristics. These types include spiral galaxies, like our Milky Way, are characterized by their flat, rotating disks with spiral arms. The Milky Way, for example, has a diameter of approximately 100,000 light-years and contains 100 to 400 billion stars. The spiral arms are regions of active star formation, where gas and dust collapse to form new stars. Elliptical galaxies are more rounded or oval in shape and contain older, less active stars. They typically have little gas and dust, meaning that star formation has largely ceased. Giant elliptical galaxies, such as M87 in the Virgo cluster, can span over 1 million light-years in diameter, Irregular galaxies lack a defined shape and often appear chaotic. These galaxies are typically smaller and may have been distorted by gravitational interactions with other galaxies. Examples include the Large Magellanic Cloud and Small Magellanic Cloud, which are satellite galaxies of the Milky Way. The evolution of galaxies is driven by a combination of internal and external processes. Star formation, supernova explosions, and black hole activity play significant roles in shaping galaxies from within, while galaxy mergers and interactions with neighboring galaxies influence their evolution from the outside. For example, the Milky Way is currently interacting with the Andromeda Galaxy, and the two are expected to collide in about 4.5 billion years, eventually merging to form a single larger galaxy. Stars are the primary source of light and energy in the universe, and their life cycles drive many of the key processes that shape galaxies and planetary systems. Stars form from clouds of gas and dust, known as molecular clouds or stellar nurseries, which collapse under the force of gravity. As the cloud collapses, it heats up, and a protostar forms at the center. Once the core of the protostar reaches a temperature of about 10 million degrees Celsius, nuclear fusion begins. Nuclear fusion is the process by which hydrogen atoms are fused together to form helium, releasing a tremendous amount of energy in the form of light and heat. This energy counteracts the force of gravity, stabilizing the star and marking the beginning of the main sequence phase of its life. Stars come in different types, classified according to their mass, temperature, and luminosity. The most common classification system is the Harvard Spectral Classification, which ranks stars from the hottest and most massive, Type O, to the coolest and least massive, Type M. The types of stars include O-type stars. These are the hottest and most massive stars, with surface temperatures exceeding 30,000 degrees Celsius. They are blue in color and extremely luminous, but they have very short lifespans of just a few million years. An example of an O-type star is Zeta Puppis, located about 1,090 light-years from Earth. B-type stars. These stars are slightly cooler than O-type stars, with surface temperatures between 10,000 and 30,000 degrees Celsius. They are blue-white in color and have short lifespans, typically less than 100 million years. A-type stars. These are white stars with surface temperatures between 7,500 and 10,000 degrees Celsius. They are more common than O and B-type stars, but still relatively rare. Sirius, the brightest star in the night sky, is an A-type star located just 8.6 light-years away. F-type stars. These stars are yellow-white, with surface temperatures between 6,000 and 7,500 degrees Celsius. They have lifespans of several billion years. G-type stars. These are yellow stars with surface temperatures between 5,000 and 6,000 degrees Celsius. Our Sun is a G-type star with a surface temperature of about 5,500 degrees Celsius. G-type stars are common and have lifespans of about 10 billion years. K-type stars. These are orange stars with surface temperatures between 3,500 and 5,000 degrees Celsius. They are cooler and less massive than the Sun, but still capable of hosting habitable planets. M-type stars. Also known as red dwarfs, these are the coolest and most common type of star in the universe. They have surface temperatures below 3,500 degrees Celsius and can live for trillions of years. Proxima Centauri, the nearest star to the Sun at a distance of 4.24 light-years, is an M-type star. The life cycle of a star depends on its mass. Low-mass stars, like red dwarfs, burn their fuel slowly and can live for trillions of years. In contrast, high-mass stars, such as O-type and B-type stars, burn their fuel quickly and have short lifespans. When a star exhausts its hydrogen fuel, it leaves the main sequence and begins to fuse helium into heavier elements. For a star like the Sun, this marks the beginning of the red giant phase, during which the star expands and cools as helium fusion occurs in its core. The Sun is expected to enter the red giant phase in about 5 billion years, at which point it will expand to engulf the inner planets, including Earth. After the red giant phase, low-mass stars shed their outer layers, creating a planetary nebula and leaving behind a white dwarf, a dense, Earth-sized remnant of the star's core. White dwarfs no longer undergo fusion and will eventually cool and fade over billions of years. For high-mass stars, the end of their life cycle is far more dramatic. When a high-mass star exhausts its nuclear fuel, its core collapses, triggering a supernova explosion. Supernovae are among the most powerful events in the universe, releasing more energy in a few seconds than the Sun will emit over its entire lifetime. The remnants of a supernova may form either a neutron star or a black hole, depending on the mass of the original star. Neutron stars. These are incredibly dense objects, with a mass greater than the Sun, packed into a sphere just 10 to 20 kilometers in diameter. Neutron stars are so dense that a sugar cube-sized amount of their material would weigh as much as all of humanity. Black holes. If the core of the supernova is massive enough, it collapses into a black hole, a region of space where gravity is so strong that not even light can escape. The first direct image of a black hole, located in the galaxy M87, was captured by the Event Horizon Telescope in 2019. Planets form as a byproduct of star formation. When a star forms from a collapsing cloud of gas and dust, the leftover material that does not become part of the star forms a rotating disk around it. This disk, known as a protoplanetary disk, is the birthplace of planets. The process of planetary formation involves the gradual accumulation of dust and gas into larger and larger bodies through collisions and gravitational attraction. Planetesimals. Small solid objects called planetesimals form within the protoplanetary disk. Over time, these planetesimals collide and merge, forming larger bodies called protoplanets. Accretion. As protoplanets grow, they continue to accrete more material, eventually clearing their orbits of debris. This process can take millions of years and results in the formation of fully fledged planets. There are two main types of planets. Terrestrial planets. These are rocky planets like Earth, Mars, Venus, and Mercury. They form in the inner regions of the protoplanetary disk, where temperatures are high enough to prevent the accumulation of gas, leaving only rocky material to form planets. Gas giants. Planets like Jupiter and Saturn are gas giants. They form in the outer regions of the protoplanetary disk, where temperatures are low enough for gases like hydrogen and helium to condense and accumulate around a solid core. In recent decades, the discovery of exoplanets, planets that orbit stars outside our solar system, has revolutionized our understanding of planetary formation and the diversity of planetary systems. The first confirmed exoplanet was discovered in 1992 by astronomers Alexander Wolszczan and Dale Frail around a pulsar. Since then, more than 5,000 exoplanets have been detected using various methods, including the transit method and radial velocity method. The Kepler Space Telescope, launched by NASA in 2009, has been instrumental in the discovery of thousands of exoplanets. Kepler used the transit method, which detects the dimming of a star's light as a planet passes in front of it, to identify potential exoplanets. Kepler's mission revealed that planets are common throughout the universe, and many stars are likely to have planetary systems. Exoplanets, or planets that orbit stars beyond our solar system, exhibit a vast diversity in their characteristics, varying in size, composition, and distance from their host stars. Some exoplanets are small and rocky, resembling Earth, while others are enormous gas giants that orbit much closer to their parent stars than any planet in our solar system. These planets are categorized based on several factors, such as their physical composition, size, and the nature of their orbits. Earth-sized rocky exoplanets, for instance, are made primarily of rock and metal, similar to Earth, Mercury, Venus, and Mars. These planets tend to have solid surfaces, making them interesting targets for further study, as they might be capable of supporting liquid water under the right conditions. In contrast, gas giants, like Jupiter and Saturn in our solar system, are composed mostly of hydrogen and helium and are typically much larger. Gas giants often have no solid surfaces, and depending on their proximity to their stars, can fall into the category of hot Jupiters, where their orbits bring them very close to their stars, resulting in extremely high surface temperatures. One of the most significant focuses in the study of exoplanets is the search for potentially habitable worlds. These are planets that exist within the so-called habitable zone of their stars, sometimes referred to as the Goldilocks zone. This zone is the region around a star where conditions are not too hot and not too cold, allowing for the possibility of liquid water to exist on the planet's surface, a critical ingredient for life as we know it. Planets found within this zone are of great interest to astronomers and astrobiologists because under the right circumstances, they might support life. The discovery of such planets has been made possible thanks to significant advancements in telescope technology and space missions, such as NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS. These missions have been instrumental in identifying thousands of exoplanets, some of which reside in the habitable zone of their stars. Among the many exoplanets discovered, certain ones stand out due to their proximity to Earth and their potential for habitability. One notable example is Proxima Centauri b, which is located just 4.24 light-years away from Earth. Proxima Centauri b orbits the star Proxima Centauri, the closest known star to the Sun, and resides within its star's habitable zone. Although Proxima Centauri is a red dwarf star, which emits much less energy than our Sun, Proxima Centauri b's proximity to the star allows for the possibility that it could maintain surface temperatures suitable for liquid water. However, the planet is also subject to intense stellar flares from its parent star, which might challenge its ability to retain an atmosphere, one of the key factors in sustaining life. Another fascinating candidate is Kepler 452b, located approximately 1,400 light-years from Earth. Kepler 452b orbits a star that is very similar to our Sun, and its position within the star's habitable zone makes it a compelling target for researchers searching for Earth-like conditions. Kepler 452b is roughly 60% larger than Earth, placing it in a category known as super-Earths, which are planets larger than Earth, but smaller than gas giants like Neptune. Its size suggests that it may have a rocky surface, and its orbit places it in the habitable zone, where temperatures could allow for liquid water to exist. The discovery of Kepler 452b has been significant because it represents a planet that could potentially offer conditions similar to those on Earth, particularly because it orbits a Sun-like star. The identification of such potentially habitable exoplanets is critical in the broader search for extraterrestrial life. Liquid water is considered essential for life, and finding planets where water could exist in liquid form increases the chances of discovering biological activity beyond our solar system. Although no definitive evidence of life has been found on these planets, the fact that they exist in their stars' habitable zones makes them prime candidates for further study with future missions and advanced observational tools. As research continues, astronomers hope to learn more about the atmospheres, surface conditions, and potential habitability of these intriguing exoplanets. The search for habitable exoplanets and the possibility of life beyond Earth is one of the most active areas of research in astronomy today. Missions like NASA's James Webb Space Telescope, launched in 2021, are expected to provide even more detailed observations of exoplanets and their atmospheres. bringing us closer to answering the age-old question of whether we are alone in the universe. The formation of galaxies, stars, and planets is a complex process that has shaped the universe over billions of years. Galaxies form from the gravitational collapse of dark matter and ordinary matter, while stars form from the collapse of gas clouds and undergo life cycles that range from billions to trillions of years, depending on their mass. Planets form in the protoplanetary disks around stars, and the discovery of thousands of exoplanets has revealed that planetary systems are common throughout the universe. The study of these cosmic components continues to provide insights into the origins of our solar system and the potential for life on other worlds. The Renaissance and the scientific revolution were critical periods in human history, marking a shift in intellectual thought that would forever change the trajectory of science, art, and philosophy. This transformation took root in Europe in the 15th century, when scholars began to rediscover and revive the knowledge of ancient civilizations, particularly the Greeks and Romans. However, unlike the earlier eras of classical antiquity, the Renaissance emphasized empirical observation, critical inquiry, and the application of mathematics to the natural world. This laid the groundwork for the scientific revolution, which unfolded over the next few centuries, and introduced a fundamental shift in how humanity understood the universe. The Renaissance was a period of rebirth that reawakened a passion for learning, exploration, and discovery. It was characterized by a growing interest in classical knowledge, particularly that of ancient Greece and Rome. Scholars began to challenge the intellectual dominance of the Catholic Church, which had held sway over European thought for centuries. The study of texts by Aristotle, Ptolemy, and other ancient scholars became widespread, leading to new interpretations and analyses of their works. This engagement with classical thought spurred developments in art, literature, architecture, and, importantly, the natural sciences. However, as thinkers delved deeper into these classical texts, they began to notice contradictions and gaps in the explanations provided by ancient authorities. This questioning of traditional knowledge led to an intellectual awakening, where observation and experimentation began to take precedence over pure reasoning and philosophical speculation. One of the earliest figures to challenge the established worldview was Nicholas Copernicus, who is often credited with initiating the scientific revolution. Copernicus, a Polish mathematician and astronomer, proposed a heliocentric model of the universe in his seminal work, De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, published in 1543. This was a radical departure from the geocentric model that had been widely accepted since the time of Ptolemy in the 2nd century CE. In Ptolemy's model, the Earth was considered the center of the universe, with the sun, moon, planets, and stars revolving around it in circular orbits. This geocentric model was deeply intertwined with the religious views of the time, particularly within Christianity, which held that humanity and Earth were at the center of God's creation. However, Copernicus proposed that the sun, rather than the Earth, was at the center of the known universe, with Earth and the other planets orbiting the sun in circular paths. While Copernicus retained many of Ptolemy's ideas, such as the use of epicycles, small circles within larger circular orbits, his heliocentric model provided a simpler and more elegant explanation for certain astronomical phenomena, particularly the retrograde motion of planets like Mars. In the geocentric model, the backward motion of planets required complex adjustments, but in the heliocentric model, this retrograde motion could be explained as a result of the relative positions and motions of Earth and the other planets as they orbited the Sun. Despite the profound implications of Copernicus's work, his ideas were not immediately accepted. The Catholic Church, which was the dominant intellectual and religious authority in Europe, resisted the heliocentric model because it contradicted the scriptural view of the universe. According to the Church, the the Earth was immobile at the center of the cosmos, as described in various biblical passages. Copernicus's model, by displacing Earth from this central position, challenged both the theological and philosophical notions that humanity occupied a privileged place in the universe. Consequently, Copernicus's ideas were largely ignored or dismissed during his lifetime. However, they laid the groundwork for future astronomers and physicists to build upon. One of the most important figures to refine and expand upon Copernicus's work was Johannes Kepler, a German mathematician and astronomer. Kepler, who worked with the precise astronomical observations of Danish astronomer Tycho Brahe, developed a new understanding of planetary motion that addressed some of the shortcomings in Copernicus's model. In contrast to Copernicus, who assumed that planets moved in perfect circles, Kepler discovered that the planets moved in ellipses with the sun at one focus. This was a monumental breakthrough in astronomy. Kepler's laws of planetary motion, first published between 1609 and 1619, revolutionized the way the heavens were understood. His first law, the law of ellipses, showed that planets do not travel in circular orbits, but in elliptical paths. His second law, the law of equal areas, stated that a line connecting a planet to the sun sweeps out equal areas in equal times, meaning that planets move faster when they are closer to the sun and slower when they are farther away. Finally, his third law, the law of harmonies, established a relationship between the distance of a planet from the sun and its orbital period. Kepler's laws provided a precise mathematical description of planetary motion and helped explain the observations that astronomers had been struggling to reconcile with the geocentric model. These laws replaced the complex system of epicycles used in Ptolemaic astronomy, simplifying the understanding of celestial motion. Kepler's work also laid the foundation for Isaac Newton's theory of universal gravitation, which would later provide a comprehensive explanation for the forces governing the motion of planets and other celestial bodies. At around the same time as Kepler was formulating his laws, Galileo Galilei was making groundbreaking observations that further bolstered the heliocentric model. In 1609, Galileo built his own telescope and became one of the first to use it for astronomical purposes. His observations transformed the field of astronomy. Among his most significant discoveries was the observation of Jupiter's moons, Io, Europa, Ganymede, and Callisto, in 1610. These moons orbited Jupiter, showing that not all celestial bodies orbited the Earth, as the geocentric model claimed. This was direct observational evidence that challenged the traditional view of the cosmos. Galileo also observed the phases of Venus, which provided further proof that Venus orbits the Sun, not Earth. Additionally, his studies of the moon's craters and mountains demonstrated that celestial bodies were not perfect spheres, as Aristotle had suggested. His observations of sunspots further challenged the notion that the heavens were immutable and unchanging. Galileo's discoveries were revolutionary, but they brought him into conflict with the Catholic Church, which condemned heliocentrism as heretical in 1616. Despite being warned not to promote or teach heliocentrism, Galileo published dialogue concerning the two chief world systems in 1632, a work that advocated for the Copernican model. This led to his trial by the Inquisition in 1633, where he was forced to recant his views and spent the remainder of his life under house arrest. Galileo's use of the telescope to gather observational evidence not only provided strong support for the heliocentric model, but also emphasized the importance of empirical observation in science. His work laid the foundation for the scientific method, a systematic approach to inquiry that involves observation, experimentation, and the formulation of hypotheses. This method would become the cornerstone of modern science, distinguishing it from earlier methods of understanding based on philosophical speculation or religious doctrine. The culmination of the scientific revolution came with the work of Isaac Newton, whose formulation of the laws of motion and universal gravitation provided a comprehensive explanation of the forces governing the cosmos. In 1687, Newton published Philosophia Naturalis, Principia Mathematica, the mathematical principles of natural philosophy, which synthesized the work of Copernicus, Kepler, and Galileo into a unified theory of how objects move both on Earth and in the heavens. Newton's three laws of motion explained how objects behave under the influence of forces. An object at rest stays at rest, and an object in motion stays in motion, unless acted on by a force. Force equals mass times acceleration, F, ma. And for every action, there is an equal and opposite reaction. In addition to his laws of motion, Newton's law of universal gravitation showed that the force of gravity is proportional to the mass of two objects and inversely proportional to the square of the distance between them. This law demonstrated that the same force that causes an apple to fall to the ground also governs the motion of the planets around the sun. Newton's work unified celestial and terrestrial mechanics, marking the birth of classical physics. His contributions not only confirmed the heliocentric model, but also provided a framework for understanding the universe as a mechanical system governed by mathematical laws. This mechanistic view of the universe would dominate scientific thought for centuries and would influence fields ranging from astronomy to engineering. The heliocentric model, first proposed by Copernicus, fundamentally altered humanity's understanding of the cosmos and our place within it. By displacing Earth from the center of the universe, it challenged the long-held belief that humanity occupied a privileged position. This idea would later influence Enlightenment thinkers such as Immanuel Kant and David Hume, who explored the implications of a vast, mechanistic universe governed by natural laws rather than divine intervention. The shift from a geocentric to a heliocentric worldview marked a profound transformation in human thought, one that laid the foundation for the modern scientific approach to understanding the natural world. In the early 20th century, the next major revolution in cosmology came with the development of relativity by Albert Einstein. Einstein's theories of special and general relativity fundamentally changed our understanding of space, time, and gravity. In 1905, Einstein published his theory of special relativity, which introduced the idea that the laws of physics are the same for all observers, regardless of their motion, and that the speed of light is constant for all observers. This led to several important conclusions, including the equivalence of mass and energy, expressed by the famous equation E mc2. Special relativity also showed that time and space are not absolute, but are relative to the observer's frame of reference. In 1915, Einstein expanded on this work with his theory of general relativity, which provided a new understanding of gravity. Rather than describing gravity as a force between objects, as Newton had, Einstein proposed that gravity is the curvature of space-time caused by mass and energy. Massive objects like the sun bend the fabric of space-time, and this curvature dictates the motion of planets and other celestial bodies. General relativity was confirmed by several key experiments, including the 1919 solar eclipse observed by British astronomer Arthur Eddington, which provided the first direct evidence of space-time curvature. This discovery made Einstein a global scientific celebrity and established general relativity as the new foundation for modern cosmology. In the 20th century, observatories like the Mount Wilson Observatory in California and the Palomar Observatory played a key role in the development of modern astronomy. At Mount Wilson, Edwin Hubble used the 100-inch Hooker telescope to discover the expansion of the universe, one of the most important breakthroughs in cosmology. The launch of space-based observatories in the late 20th century further revolutionized our understanding of the cosmos. The Hubble Space Telescope, launched by NASA in 1990, provided unprecedented images of distant galaxies, nebulae, and other celestial objects, helping astronomers refine their models of the universe. Hubble's observations of distant supernovae also provided strong evidence for the existence of dark energy, a mysterious force driving the accelerated expansion of the universe. Other space telescopes, such as the Chandra X-ray Observatory, 1999, and the James Webb Space Telescope, 2021, continue to push the boundaries of observational astronomy, allowing scientists to probe the early universe, study the formation of galaxies, and search for signs of life on distant exoplanets. The development of radio astronomy, infrared astronomy, and gravitational wave detection has also expanded our ability to observe the universe in new ways. In 2015, the LIGO Observatory detected gravitational waves for the first time, confirming another key prediction of Einstein's general relativity and opening a new window into the study of black holes, neutron stars, and the most violent events in the universe. One of the most profound discoveries of 20th century physics was the realization that the laws of the quantum world, the physics of the very small, govern the behavior of particles and fields in the early universe. Quantum mechanics, the branch of physics that deals with subatomic particles, provides insights into the universe's origins, particularly through the concept of quantum fluctuations. In classical physics, nothingness is considered an empty vacuum, devoid of matter or energy. However, quantum mechanics reveals that even in a vacuum, space is never truly empty. Quantum fluctuations are spontaneous, short-lived changes in the energy of a point in space, and they result in the temporary creation of particle-antiparticle pairs that pop in and out of existence. These fluctuations are caused by the Heisenberg uncertainty principle, formulated by Werner Heisenberg in 1927, which states that we cannot know both the position and momentum of a particle with absolute certainty. This uncertainty leads to inevitable fluctuations in energy, even in the vacuum of space. Quantum fluctuations played a crucial role during the early moments of the universe, particularly during the period of cosmic inflation, a brief yet rapid expansion of space that occurred within the first 10 to 1032 seconds after the Big Bang. The theory of cosmic inflation was first proposed by Alan Guth in 1980, and it posits that the universe expanded exponentially in size during this incredibly short period. During inflation, quantum fluctuations were stretched to macroscopic scales by the expansion of space. These fluctuations in the density of matter and energy later became the seeds for the formation of galaxies, clusters of galaxies, and the large-scale structure of the universe. The theory of inflation predicts that these fluctuations would leave imprints in the cosmic microwave background, CMB radiation, the afterglow of the Big Bang, which we observe today. In 1992, the COBE satellite detected tiny variations in the temperature of the CMB, providing strong evidence for the inflationary model and the role of quantum fluctuations in shaping the universe's structure. These fluctuations explain why galaxies and other cosmic structures are not distributed uniformly across the universe. Instead, there are regions of higher density where matter clump together to form galaxies, and regions of lower density which are more empty. The fluctuations were tiny, on the order of 1 part in 100,000, but after billions of years, they led to the diverse and complex cosmic structures we observe today. The quantum vacuum is a key concept in understanding how particles and fields behaved in the early universe. In classical physics, a vacuum is a completely empty space with no matter, but quantum mechanics introduces the idea of the quantum vacuum, which is filled with fluctuating energy and virtual particles. Even in what we perceive as empty space, particles and antiparticles, such as electrons and positrons, are constantly being created and annihilated in pairs. These particles are called virtual particles because they exist for only a fleeting moment, borrowing energy from the quantum vacuum and disappearing almost immediately. The energy fluctuations in the quantum vacuum lead to the spontaneous creation of particles, a process that is described by quantum field theory. According to this theory, fields, such as the electromagnetic field, exist everywhere in space, even in the absence of matter. Particles are excitations or disturbances in these fields, and quantum fluctuations can cause these disturbances to appear temporarily, creating virtual particles. Although these virtual particles cannot be directly observed, their effects can be measured. One of the most famous consequences of virtual particles is the Casimir effect, discovered by Hendrik Casimir in 1948. The Casimir effect occurs when two uncharged parallel metal plates are placed close together in a vacuum. Due to the fluctuations in the quantum vacuum, there is a difference in the energy density between the space inside and outside the plates, creating a measurable force that pushes the plates together. This phenomenon is a direct result of quantum fluctuations in the vacuum. In the context of the early universe, particle creation from the quantum vacuum had a significant impact on cosmic evolution. During the inflationary period, the rapid expansion of space amplified these fluctuations, leading to the production of real particles from the quantum vacuum. These particles eventually cooled and condensed to form the matter that makes up the galaxies, stars, and planets we see today. The idea that particles can emerge from the quantum vacuum has profound implications for cosmology. It suggests that the universe itself could have emerged from nothing, a quantum vacuum. This idea, first proposed by physicists such as Stephen Hawking and James Hartle in the 1980s, posits that the universe could have been born from a quantum fluctuation in the vacuum, without the need for a prior cause or a pre-existing state of matter. This notion challenges classical views of causality and the need for a definitive starting point for the universe. Stephen Hawking, one of the most influential theoretical physicists of the 20th century, made a groundbreaking discovery in 1974 that linked quantum mechanics to black hole physics. Hawking demonstrated that black holes are not entirely black, but emit radiation due to quantum effects near their event horizons.